Automated testing in virtual and real environments can help you reduce hardware integration times and significantly facilitate validation and verification. High reusability of test cases and simulations enables a seamless transition from software-in-the-loop to hardware-in-the-loop testing. Based on a point object controller, I will outline some basic strategies for efficient testing, from digital twins to acceptance tests. Hi, my name is Manuel. I'm a strategic customer consultant at Vector, involved in functional and security testing of railway systems, such as signaling systems and onboard equipment. Vector tools, such as our system-level test tool Canoe, can be used for testing embedded software of all kinds of systems. These include signaling systems, such as interlockings, object controllers, and the field elements themselves, as well as equipment inside trains, such as control units of brakes and motors. Typical use cases of our test tool include testing of the Ethernet protocols PDI and Raster as part of the SCI protocol, OPCOA as part of the SDI and SMI interfaces in railway signaling, and TRDP for use inside trains. In this session, I will explain testing concepts and strategies on the example of developing a point object controller. I have chosen this example because it is simple to understand, as it only requires the knowledge that a point can move into a left and right position, and that the interlocking is responsible for triggering a movement. The object controller itself translates the digital communication of the interlocking into a language the point motor understands. This could be digital I/Os or other kinds of network communication such as CAN. But before we dive into the topic, let's remind ourselves why efficient testing is a very important issue. At its core, testing is about ensuring safety. For example, even a minor fault in the software of this object controller can have devastating and life-threatening results, such as a derailed passenger train. It is the most obvious reason for rigorous testing and ultimately creates the obligation for manufacturers to comply with strict safety standards and norms, such as the EN 50716. Besides common sense and compliance with standards, testing becomes more important with increasing modularization of systems. Initiatives such as U-Links drive the standardization of interfaces, which will lead to increased competition and higher levels of integration. Testing components thoroughly is the only way to avoid troubles during the integration process. Given the critical nature of railway systems and the increased integration complexity, efficient testing strategies become imperative. I want to emphasize that testing can also be quite valuable during development. While unit testing of the code is a requirement set by multiple norms and standards, system-level testing of the software can provide early feedback, which helps to identify potential issues at a time when resolving them is cheap and requires little effort. Thereby, test-driven development reduces costs and time to market. It also encourages developers to write cleaner, more modular code, as we will see later when we go into the technical details of system-level testing. It can also reveal shortcomings in the requirement specification. So, what kind of testing strategies can help us to meet those demands and allow us to maximize the benefits? Well, one thing is quite clear. Manual testing is not only slow and costly, but also inconsistent and prone to errors. Therefore, automated testing plays a vital role in modern development processes. By automating repetitive and time-consuming tasks, we can reduce human error, increase test coverage, and accelerate the testing process. This leads to significant time and cost savings, allowing developers to focus on more complex issues and deliver high-quality products faster. Moreover, automated tests can be integrated into continuous integration pipelines, ensuring that your latest changes do not introduce unwanted bugs. Let's turn back to our example, the object controller. As you can see, I do not have an electronic interlocking or a point motor with me. Luckily, I do not need these components to verify the object controller's behavior. Actually, I would not even need the physical hardware of the object controller itself to verify its behavior. But I'm getting ahead of myself. Instead, a virtual representation of the physical system, also known as digital twin, can be used to simulate the missing counterparts of our device under test. This concept is known as hardware-in-the-loop testing, or HIL in short. With HIL, I can validate the system's behavior and ensure that hardware and software work together as intended across various scenarios. As the simulation provides precisely known initial states and straightforward means of manipulating its behavior, the concept offers a high degree of repeatability during the testing phase. Being able to run tests on selected components before the entire physical system of the environment is available is a major advantage of using environment simulations rather than the real communication partners. Therefore, compatibility problems between different modules are revealed early in the development cycle, which can save valuable time and protect you from many troubles. Additionally, HIL tests mitigate the risk of damaging expensive equipment by allowing engineers to test scenarios and edge cases in a controlled virtual environment. By testing the software that is running in a virtual environment itself, rather than on hardware such as an evaluation board, we can perform tests even more securely. But once again, I'm getting ahead of myself. Of course, setting up your virtual environment requires some dedication and time investment. Imagine two development teams. One develops a component A, and the other develops a second component B. These two components need to exchange data in the final system. A and B could be individual control units inside a train, or an object controller and the interlocking for a section of a track at a train station. If the two components are only ever exchanging data when both devices are available as hardware and errors are found, it is very costly to update the system. If, on the other hand, each component had been tested against the simulation of the other device or its full virtual environment, hardware integration issues are much less likely. Therefore, the virtual environment will save time in later phases of development, which will reduce your time to market. Each component tested in a virtual environment reduces the hardware integration time drastically. With such a virtual environment at hand, we could go even further and integrate HIL into our CI/CD pipeline, where tests are executed whenever a change has been made to the software. With sophisticated tools, the test framework can be easily expanded. For example, if we later realize that a temperature sensor is required, we can simply simulate it within our test tool. These simulations can not only be used for hardware testing, as I have hinted at several times already. Instead, we can use them much earlier during development, even if we do not have any hardware available yet. This approach is called software-in-the-loop testing, or SIL. SIL is a simulation-based testing technique where the embedded software is executed on a host machine, typically the developer's computer, rather than on the target hardware. This early-stage testing without hardware allows developers to validate software logic, control algorithms, and communication protocols, and ensures that the core logic is robust and compliant with specifications before moving to more expensive test stages. The developers and software testers can inject faults, simulate edge cases, and verify communication protocols, all without needing physical hardware. There is another major advantage of SIL. It is not bound to real time. Developers can speed up time and run thousands of tests in minutes, enabling fast feedback loops and allowing them to verify the correct behavior of the software over a long period of time. This way, memory leaks and other errors that would occur only after several months of operation can be found within a matter of minutes. For our point object controller here, the logic is rather simple, and one could argue whether SIL offers true benefits here. But keep in mind that the situation changes dramatically when we think of an object controller for a level crossing. For our SIL scenario, we need the core logic compiled to run on a PC and our environment that consists of a digital twin of 1, the point motor, including mechanical delay, position feedback and failure modes, and 2, the interlocking system that sends commands and receives status updates from the object controller. We can imagine various test scenarios. Normal operation, switch from left to right and back again. Fault injection, simulate a stuck motor or delayed feedback. Communication loss, test the controller's behavior when interlocking messages are delayed, dropped or corrupted. In this way, we can verify that the controller sends the correct commands and handles errors gracefully, for example retries and timeouts. Of course, we can test this behavior with the real device in hill testing also, but preceding SIL testing offers a few advantages. First and foremost, debugging is much easier in a virtual environment. Also, the code can be adapted much quicker, as it does not require flashing the software to the microcontroller. Furthermore, this approach does not require every developer to have a physical device with them. Overall, we achieve improved modularity and easier maintenance with SIL. As we have a clear separation of application logic and hardware drivers, otherwise we would not be able to test the logic separately, we get a much more structured software architecture. By abstracting hardware details, SIL testing allows developers to focus on software functionality, leading to more robust and reliable systems. It also enables earlier feedback, reducing development time and costs. SIL is not meant as a replacement for hill. It is necessary to include hardware components such as drivers in our tests. However, since the requirements and the environment of the core logic are identical in SIL and hill, test cases can be reused without modifications. By combining SIL and hill, we create a comprehensive testing strategy that covers both software and hardware aspects of our system. This dual approach not only enhances the reliability and robustness of our system, but also accelerates the development cycle by enabling continuous testing and integration. In this way, hardware and software can be developed in parallel, speeding up the overall timeline. When we want to reuse test cases across different environments like SIL and hill, we should introduce an I/O abstraction layer in the software under test and in the test tool. Within the software under test, this abstraction is a software layer that provides a consistent interface between the application logic and the underlying hardware. It abstracts away the hardware-specific details, allowing the same application code to run on different platforms, for example simulations, emulators or a real hardware, without modification. An I/O abstraction layer simplifies interactions with complex systems by hiding intricate details behind a straightforward interface. This approach allows developers to focus on higher-level functionality without worrying about the underlying hardware specifics. In the logic layer, the point can only be in left or right position and receive a command to move. The hardware drivers, on the other hand, only care about some payload of an Ethernet package or certain voltage levels of their I/Os. The I/O abstraction layer connects these different views. It enhances modularity and make systems easier to maintain and upgrade. Let us summarize our workflow. We begin by creating a virtual environment and implementing our test cases. These are first executed in a SIL scenario to validate software behavior during development. The same tests are applied in a HIL scenario, which complements the development process and can serve as an end-of-line test. By reusing test cases, automating execution, and validating across virtual and physical environments, we can build robust embedded systems faster and with greater confidence. How can we support you in implementing automated testing for your development projects? At vvERED25, we offer sophisticated tools that support you in every phase of the development process, from static code analysis and unit testing to SIL and HIL. And most importantly, you can do SIL and HIL testing in one single tool. With vector tools, you can perform tests in server-based applications, create traceability matrices by linking test cases to requirements from ALM tools, and get automatically created test reports to lower V&V efforts on your side. So, let's get in touch and talk about your use cases. That is all from my side. There are many more interesting tutorials on HIL and SIL testing, Canoe and other topics on the vvERED25 Tech Tutorial channel. Subscribe now and activate notifications to not miss new videos.